Hello, guys. So welcome to this lecture. This is a video on power series. We've already looked at infinite series, infinite sequences and series. So this one is going to capture the power series bit of this lesson. Okay. So we'll look at the definition of what a power series is, and then we'll look at radius and interval of convergence. And then how do you actually represent a function as a power series? So given any function, how do you represent it as a power series? After that, we'll look at the differentiation and integration of power series. And then actually 3 and 4 are linked, right? Once you know how to differentiate and integrate power series, it helps you to be able to represent given functions as power series. And then we'll look at Taylor series and Taylor polynomials. How in general, given a function, how do you represent it? And then how do you actually show that the function or the series that you obtain actually represents the function that you've been given. Okay, so that is what we're going to do in the next couple of minutes. So this will probably cover a couple of videos. So watch out for different parts of the video. Okay. Okay, good. So here's a definition for what a power series is. A power series is an infinite series that is of this form. So a power series centered at A. So the center is A. A is some number that you know. The center could be 0, could be 1, could be 2. But the difference between what we have here and what we've looked at so far is that now you have this variable x, right? Or you have this x. X minus A10, right, in the series. That is what makes it a power series. So you have a variable x here in there. Okay. Now these constants, these coefficients here, Cn's are very important, right? Once you write the series in this form with the different terms, if you know what these coefficients are, the Cn's, then of course you know what the power series is. That is basically what you need. So often when you find a power series, you also want to be able to compute what Cn's are. So in any case, that is the definition for a power series. Here's a simple example of that and a very important one. If the center is 0, if A is 0 and Cn is 1, right? Every constant, every coefficient here is 1, then this guy reduces, right? This guy is 0, so this goes to 0. So this series reduces to a series. This is a geometric series. Reduces to this geometric series given by this, where you have 1 plus x squared plus x cubed all the way x to the n to infinity. Because it's a geometric series, we know how to sum geometric series. It's just basically, so remember, I'll come back to this. Remember, for a geometric series, you have the series AR to the n, if n starts from 0 a to the n. Well, you could leave it as this, right? Then you're going to have a plus AR plus AR squared and so on, right? And we know that this sums to A over 1 minus R, right? Where R is the radius, the ratio, and the series converges when absolute value of R is less than 1. Okay, so this we know. So you're going to use that idea a lot, okay, in here. Okay, so this is a geometric series. The first term A is 1, so you have 1 over 1 minus x. The ratio R is x in this case, so you have 1 over 1 minus x. And then the series converges when the ratio absolute value of x is less than 1, and that is what you have here. So you have a geometric series, which is an example of a simple power series. What this also means is that given the function 1 over 1 minus x, I can represent this as this series. Okay, I can say that if I have the function 1 over 1 minus x, this function is actually equal to this series, the series x raised to the power n from 0 to infinity. You see? So given a function like this, I can actually write it like that as a series. Okay, so we are going to exploit this idea, this thing here. We are going to exploit it to be able to write different functions in terms of power series. Okay, so the next couple of slides will tackle that idea. But before that, we want to look at what we mean by the radius of convergence and the interval of convergence of a series. Then we'll come to this idea. All right. Okay, good. So this theorem captures what a radius of convergence and what the interval of convergence is. For a given power series, which is given by this, there are three possibilities. Either the series will converge only at the center when x is equal to a, right? Then this one converges. Or the series will converge for all values of x, right? For all real. Or often what you'll find is a third case where the series will converge within some interval, right? What is known as an interval of convergence. So x minus a, the absolute value of that less than r, is the interval of convergence. And it will diverge away from this interval, okay? So often you want to be able to tell what this radius is. And later on, I'll show you how you actually compute this radius to tell you the interval within which the series will converge. Okay, good. Often you often use the ratio test that we looked at or the root test. You can use those to find what the radius of convergence is. Okay, and if you have the interval, so this is what the interval means. It says that the interval of convergence is x minus a less than r. Of course, this means that x minus a, right, lies between negative r and r. Okay, and then if you add a to both sides, or you can bring a and a to that side, that means that a minus r is less than x less than a plus r, right? So x lies in this interval. So that is the interval of convergence. So if you have your center, you have x, this is a, as your center, x will lie from a minus r to a plus r. From here to there is your radius, okay, of convergence. And all of this from here to there is the interval of convergence, okay? So it means that for given a, if the series converges, often it will converge within an interval, or it will converge for all the real lines, which is not very common. Okay, so that is a bit about radius of convergence. I'll probably come back here and refer to it. Now, how do you compute the radius of convergence? If you're given a power series, there are a couple of ways you can do that. I'll show 3 different ways that you can do that. You can compute it using this. So these Cn's are these functions here, these coefficients, Cn, okay? So you want to find the limit as n goes to infinity of Cn over Cn plus 1, right? Find the limit, whatever you get, the result here will give you the radius of convergence. You could also use the quotient, sorry, the root test, right? The root, you find the limit as n goes to infinity over 1 over the nth root of Cn. That will give you r. Or you can find, this is basically the same as this. If you find the reciprocal of this, right? Find the limit as n goes to infinity of Cn plus 1 over Cn, then that will give you 1 over r. Okay? So the same as for this. Good. A third approach, which is quite interesting, is that you could directly use what we did when we're looking at infinite series, okay? You can find the limit as n goes to infinity of an plus 1 over an. An, okay, an, this guy, this an in this case is all of this, the whole term. That's an, okay? So if you find the limit as n goes to infinity of an plus 1 over an, the absolute value of that, and you get L. Now, remember from our study of infinite series, right? The ratio test. If you find L and L is less than 1, then the series is convergent, okay? So you can use that idea to show that if the absolute value of x minus a is less than r, well, if L is less than 1, then you have this, right? You have x minus a is less than r, where r is the radius of convergence. Okay, so you can exploit that idea. I will show an example of that to be able to find the interval of convergence and then the radius of convergence. And if L is greater than 1, then of course the series diverges. Okay, so these are some ways that you can calculate the radius of convergence or the interval of convergence if you want to. Okay, so here's a good example. You have this series from 1 to infinity, x minus 1 to the n over n. Okay, so it says for what values of x is the series convergent? So that is talking about the interval of convergence. Okay, of course, if you can find the radius, then the interval is easy, right? If suppose I know the radius of convergence, if I can compute r, let's say r is equal to whatever, let's say 10. Okay, then from the definition, the interval of convergence would just be x minus a in this case is 3. Okay, this value here, and that should be less than the radius. So this guy gives me the interval of convergence. Okay, so once you get the radius from the series, you can also find the interval of convergence. It's often very easy to find. So the radius often is the most critical one to find. Here, we want to use a third approach to find the interval and of course, also the radius. So an will be all of this. So you find the ratio an plus 1 over an. That's going to be given by this, right? This is the same as x minus 3 raised to the power n multiplied by x minus 3. So x minus 3 to the n cancels this. Okay, and then of course n over n plus 1. So here you are left with a factor of x minus 3, and that is what you have here. Okay, so these n's are positives. They are just positive integers. So you can pull this out of the absolute value sign, and you have this. Okay, because we will need to take the limit. Okay, I can divide through by n and divide by n here. I get 1 over 1 plus 1 over n. Okay, so the ratio an plus 1 over n is basically this guy. So to find the limit of this is to find the limit of that is this. So as n goes to infinity, of course, this guy goes 0. So you have 1 times x minus 3, you just have x minus 3. So if you like, this guy here is our L, okay? This is L. And the theorem, right, from the ratio test says that the series converges if L is less than 1. So if you go back to what we just got, okay, the series will converge if this guy is less than 1, okay? So the series convergence for x minus 3, absolute value of that less than 1, which of course you can write as that, okay? If I pull this out, x minus 3 less than 1, of course, means that x minus 3 lies between -1 and 1. You add 3 to both sides, you're going to have 3 minus 1 here. I have x, then I'm going to have 1 plus 3. Okay, if you add 3 to each term, you're going to get that. 3 minus 1 is 2, of course. X 3 plus 1 is 4. So absolute value of x minus 3 less than 1 is the same as the interval x between 2 and 4. So for this series, it means that the series is going to converge between, if this is a 2, there's a 4 here, it will converge in this interval. Okay, from 2 to 4, or between 2 and 4. That's what it means. Okay, good. So we know the interval. Of course, from the definition of what a radius of convergence is, the radius is 1, okay? Or you could have computed the radius, right? And then you get an interval from it. This is what we show next, okay? So to compute the radius, our Cn, in this case, is 1 over n. Remember the series is this. So the series is the same as, can be written as 1 over n, okay? X minus 3 raised to the power n. So the Cn term in the general form is this, okay? So your Cn is basically 1 over n. So you can use that to compute the radius of convergence. So I have the limit, radius is the limit as n goes to infinity of Cn over Cn plus 1. That is equal to Cn is 1 over n. Because I'm dividing by Cn plus 1, I'll take multiply by the reciprocal, right? And so I'm going to have n plus 1 over 1, okay, which is n plus 1 all over n from here. Okay, so n cancels this. You have 1 plus 1 over n. Find the limit. This guy goes to 0, so you have 1. So r is equal to 1. The radius of convergence is 1. Okay, so since the radius is 1, of course, you can then find the interval if you want the interval of convergence from the series. So to get an interval from the series, you can get it. Remember, the series is this, raised to the power n all over n, or this. So from this, you get a series, okay? You get the, the radius. Remember, we said the radius is given by x minus a divided by r. Less than r. A is 3 here. So I just pick what is here, right? So I have x minus 3 is less than the radius. We just calculated the radius to be 1. So 1. So this gives me the interval of convergence. Okay? So you can get an interval from the series once you have computed what the radius of convergence is. Okay, good. So here's a second example. Is similar to what we've done. So here we go straight away to compute the radius of convergence. In this case, our Cn is this factor, minus 1 to the n all over n times 2 to the power n. Okay, you leave out this x bit, the x plus 2 raised to the power n. Okay, good. So you pick out your Cn, which is given by this. So the radius of convergence is the limit as n goes to infinity of Cn over Cn plus 1. Cn again is this. If you take the absolute value, the negative stuff go, right? So you just have 1 here. So you have 1 over n times 2 to the power n, okay? You are dividing by the Cn plus 1, so you multiply by the reciprocal. So you are replacing n with n plus 1, right? So you have n plus 1 times 2 to the n plus 1 over n. Here, this guy here, 2 to the n plus 1 is the same as 2 to the n multiplied by 2. So you can pull the 2 out. The 2 to the n here cancels the 2 to the n down here. And so this simplifies to that. Okay, so you just have 2 limit as n goes to infinity of 1 plus 1 over n. If you take the limit, this guy goes to 0. So you have 2 times 1, which is just 2. So in this case, the radius of convergence is just 2. All right, radius is 2. So the interval of convergence, which you can get by picking this guy here, absolute value of x plus 2 has to be less than the radius of convergence. So x plus 2 is less than 2. Okay. So as I said, once you compute the radius, you can easily get the interval of convergence from this x factor here, this factor here in the series. Okay. Good. So that is how you actually find how you compute the radius and the interval of convergence for a given series. In the next video, what I will do is look at how you represent functions as power series. Okay, so given a function, how do you actually represent it as a power series? That will be the next video. And then in the final one, I'll look at Taylor series and Taylor polynomials. Okay, so I'm going to end this one here, and then we'll continue right from here when I return. All right.